been a little while since I've done this, but there's a Slack channel that you can get to with the first link I have here, and someone asked yesterday about how, if you have objects stacked on top of each other and you didn't want to use physics, you wanted to figure things out by hand, and the object rotated, how you would get the object to that position and orientation, what the math involved is. And I've got some math resources that I've been trying to develop in the past. So I've been thinking I could use this to hash those out, show what's going on, and really drill down and hammer out some of the problems. So I'm going to do a preliminary one of those tonight. Maybe do some of the geometry things we were doing before, but we'll see. So I've got a blank project here. Do I have it? I have not opened it. Let's see. So there's nothing there yet. Because we have no code. Let's say we started with and put it in the middle of the screen. We'll have width of 50, height of 100. And let's make that a little wider and taller. All right. And get the color. So this will be red. Okay, and this position is the center of the rect. So we can, by, what do I want to say? So we can get half dimensions by reading the width out, dividing by 2, ditto with the height. And we can start from the rectangle's position and add those to one another. Let's see. So x2, y2 would take the rect's position and add half the width. Or take its y coordinate and then add half the height. So we could, actually I should, so x1 would be that position. Normally you wouldn't need to be quite this specific, but this is for demonstration. So we could put another say a circle with a circle. Okay, what do I do? So I can put a circle to the right and at the same height as the center, like this, with say a radius of 15 Let's see how well 15 shows up. Okay, it's actually pretty good. And give it the same color treatment. Make it green. And let's see, what's that? And a stroke. No, let's add a stroke. I don't know how well that shows up. I'll leave it at that. And another circle. With the same X position as the center of the rectangle, but the new Y coordinate, and make that one bluish. So increasing X, increasing Y, and the Y increases downward because it's computer graphics. So that's quite common. And what we have, put something else down a little further. Y3. Just keep the X the same to be in the center and start a little further down. And so that's 200, so 250. And X axis, we'll draw a line from say Y3 to X3 plus half width, Y3, and give it a stroke color. All right, so I've got a line tracking the x-axis like so. And we'll do one for the y-axis. In this case, it's x3 we want to keep the same, but we'll go half height, I should say. I don't know what colors we really want for these, but I'll vary that up too. Okay, so x-axis, y-axis. These are the typical axes we'll follow. And actually, maybe we'll just move those back up onto the rect itself. Oh wait, I can do that. And all right. So if we wanted to, from here, to put another rect up on top, at some point we could follow the x-axis for a certain number of units, then follow the y-axis, in this case in reverse, a certain number of units and put that would be that depending on how we wanted to put the object there, but assuming this is where the center goes down, like it would be this position relative to the rect, but on another rect. So we would go X number of units, then Y number of units. And then we would be in the new space of our second rectangle. So let's do something like that. So say our positions were 100 and 100, or do we want that? So the Y might be kind of maybe just a distraction at the moment, because it's for this basic test we only really want the second rectangle on top of the first one. So we'll also give this rectangle a different size. So 100, 100, and then half width 2. Half 2 would be rectangle 2's width. I'll give this another color. I don't think I used yellow yet. Okay, so to figure out these positions for the center, we'll want X4, Y4. We'll want to go from the center of the first rectangle, X1, Y1, plus X along the X-axis, and along the Y-axis, we'll just do minus half height to get us onto the base. So X4, Y4. So that would put us, we're here some, and then up this far. Then to position the rectangle itself, we'll also want to go up half of its height. So say Rect2 height equals, I guess since it's 100 here, so we'll give it 50 and then make this twice the height. Let's see if we got all that right. No, we did not. Okay, so we have an error on line. Is this visible? I don't know if there's an error, but main 44 equals expected near local. So something is, oh, because I just copy pasted these on there. They should not be there. All right, this is not quite where I wanted it to be, but because this is the half height. So I was right. So X1 minus half height. Oh, and I didn't even use it. So this is actually half height 2, and then we want 2 times half height. So Y4, which is our position on the rectangle vertically here, and then we go up a little more by half height 2. apparently have it elsewhere. Oh yeah, down here. I don't need to calculate the other one. I'm not using this. Now we get to puzzle something out. 2 times half height. So this is not as high up as it should be. Y1 is the, yeah, that's the middle of the rect, and then might not. Oh, hi, Hickory Dragon. I didn't see you there. I'm puzzling something out. Not seeing it. Let's see. Let's see. So if I just add some to this. I'm short. Let's try putting a little circle at x4, y4. And give it a radius. This was probably getting hidden. So that, okay, that's where I thought it would be. So I'm just 2 times half the height. Y4 minus, so the y4 is where I think it should be. It's right there. But I want to if I move back to that spot, I'll be there. So why is this twice as tall? Oh, that is the wrong height. Yeah. Most errors are like this. Okay. So from the center, we'll go to a spot x along, I'll put a I'll put a circle there too. Okay, so into the x4, y4, x4, y4, yeah. I keep forgetting the radius. Right. So this, from the center, we go along x units. So far, so good. And we do that by following x along the x-axis. And then from that spot, y along the y-axis. Now, normally we'll just be doing this in Euclidean coordinates. So x will be going to the right, y will be going up, or in this case, down. But we want to generalize this slightly. So let's remove that circle. And we can see this by setting the rotation to something else. So, for instance, rect 1, rotation to 30 degrees. And this breaks everything because these are in our local global coordinate system, and this we want everything in the coordinate system, the box, and the other objects. In this case, the coordinate system, the box. So we need to find we need to establish the what do I want to say? The local axes. So we'll have my mouse is giving me. So if we have one of our axes up here, and this is the normal x-axis, and we'll have some angle and this position will be cosine sine. It's all the grace of the mouse. 90 degrees from that, up here, and we can find this by plugging into some formulas. So this isn't just coming out of nowhere, but we'll have, if we have y, if we consider y as being up, then in the way it's drawn here, y will be negative, and, or I mean, sorry, y will still be positive, but x will be negative. And when you do 90 degrees, which you can find from the rotation formulas and some other things, you'll flip the two components. So we'll have sine theta cosine theta. And we know that since the x is negative, we put the sign here for this direction and keep the sign as is for the y value. If we went in the other direction, we would instead negate the cosine and keep this positive. And these are 90 degrees apart, just like x and y. The big trick here is that in our project, y is pointing down, So this will get slightly changed around, and I think some of that might be confused by the rotation tool, so I might have to try this a few times. But you will go back. So we'll first turn our angle into radians. So take that and run it through this. They're still all right. And let's use that to calculate these lines we had and see if they all line up. So we want x2 and y2, which we see here, to adhere to these axes. We'll have what would we call this? And right x, right y, close math, close should be angle. So I think we'll have to. I think we'll want to negate that, but I'll demonstrate the issue first. So yeah, in this case, we want to multiply x by right x times half width and right y times half y. So it incorporates the x-axis and the y-axis both. And let's see what we got with this so far. And so far no change. Another angle. I should put this into a this one. I don't know if that's visible. So yeah, 0.52. .6 phase R. Okay, we might need to fill in more of this information. We're seeing. And the x has moved, the y has moved. It's just not very evident. I think I might be missing a step. Oh, oh, no, that's should be okay. I'm not taking that into account in the line. Right, so what yeah, I'm doing something silly. This made sense in the case of the axis aligned values, but it doesn't make sense here because I'm just selecting one component from each of these two things, but I want the position on the right, which is going to be see, this is right vector x, right vector y. So I want the middle position plus the right vector times the half width, and the middle position plus the right vector y component times the half. Do we want that? No, I don't want to move that one up at all. I'll just have that point to the right, and then the upper point, I guess we would call it. That would be still x1, but nothing here. Y1 plus right vy times half height. And we'll put the circle. This one, I believe, yeah, this one is on the right. So let's see if that, it's moved down now. Or where has that moved? I don't think I got that right. Right dx. This might be a case where the angle is backwards. Let me see if I can. No. Oh, yeah. I want the right angle, but I still want this. This should still incorporate the y component, but it should incorporate the half width. That's what I'm doing. There we go. So now it's because we are moving to the right, so we only want to incorporate the right vector, but we're moving by half the width to the right. And we'll do likewise for this upper direction. So that will be, in this case, we don't want right, we want that direction that we showed in the drawing. So that will be up. And when we did the drawing, we used this, but we might have to switch around where we had the y component negative, the x component positive, but we flipped the x and y's. And we'll do the same thing for the up dx as we did before. So this will be up times half the height, which I botched. And again, up times half the height. And now we'll put it to use in the second circle. Okay, and as I said, it turns out it's going to go down because we need to. So I have to flip this. Flip the angle. No, that won't work the way we want it to. So let's try actually using this other, or maybe I'm trying to think if this will make it more confusing. If we want to think of that as up, maybe we should do the correction here. Yeah, I think that'll do what we want. So the points are where where we expect them to be. Now we'll fix those lines. We want the x-axis to follow the 2's, and the y-axis will be, what did I call these? I don't have anything for it yet, do I? Rx. Oh, I want Rx, that's what I want. Okay, so the x-axis goes from the center to Rx, and the y-axis should go from the center to Ux. There we go. So now these are respecting our rotation. And the next trick is to go from this position up here, x units along. And we'll do that by walking along the rotated x-axis to get there. And that's merely a matter of taking our Ux point and advancing. Do I have a circle for? No, I don't. Oh, I'll show it for testing. Okay, so I want so this is the base of the rectangle on top of our the base of our top rectangle on top of our bigger rectangle below it. So we'll go from that upper position along the right vector by x, and we'll do the same thing with the y component. So also along the vector again times x, because we're moving to the right that many units, and let's show a little circle with it. There it is. So what we wanted to do was then we want to put the rectangle on top of that, but using the local direction. So we'll adapt this bit here to start from that base position, and because follow up. Oh, and I'm forgetting that I need to do it for both. So we'll follow up by half height 2, not half height times 2. Yeah. And so its position is somewhere around here. And we also want that to have the rotation of our original rect. So we'll just assign the rotation to be rect 1 rotation. And there we go. It's flush with that. So that's half of what I wanted to show. The other part, we might instead start with this and then want to work backwards. So we might have that we know we're here. So how much x and y are we really? Because if we just get a random position, we're not going to know much of anything. But if we have the right and the up, we can work it out. So what I'm going to do is show a little bit of that math comes into it. This might be interesting because I don't know how well I can do this on the fly. So we'll start with this and clear it. I'm going to assume that the cosine and sine stuff is known, and also that the Pythagorean theorem is known that you can get an angle by, or you can get a length with x squared, y squared, and then take the square root. So if we have one direction going this way and another direction going this way, if this is a right angle, then the Pythagorean theorem tells us this length, and we can use this length up to here and the height. And we'll call this side V. Oh, that doesn't look very good. This is V. Mouse is getting snagged and not rendering so well. And this whole thing down here, W. So these are two directions. And there are differences between points. So there's a point here. You subtract this point from this point, and it gives you this displacement between points. And likewise down here. And if we took V and added to it, we would land down on W. So V plus, we could call this V plus X, but we could also call it, since we're going V plus X, instead of calling it X, we could call this W minus V, because if we add W minus V in W, we get V back. So this is, and you can work out, because these are just X and Y. If you work all this out, it actually is just addition. So we'll just assume that at the moment. If this is an angle theta, then this part here is this length, which we'll just call it for convenience V. Usually you put in little bar operators around it and everything, but so this is V cosine theta. Now even though this is in general not going to be a right triangle, this part down the middle will separate these two into right triangles. And from there we can deduce that this length will be W plus the height squared. W squared plus the height squared equals this whole thing squared. So this will give you H squared plus W minus V cos theta squared. I'm gonna run out of room here. W minus V equals, I messed that up. Let's see if I can. Yeah, equals W minus V squared. So that'll be H squared plus W squared minus 2W V cos V squared cos squared equals W squared minus 2VW plus V squared. And on this side, it's V squared equals H squared. You might be able to see where this is going slightly. Squared plus V squared cos squared. So if and this is the best way to attack this now. I think typically we'll move it. I think the H squared is we don't care about the H squared really. We can just get rid of that. So we can move this onto the other side of the equation. I apologize for this as not being growing increasingly illegible. But so h squared equals, convert these from one to the other, squared equals b squared times 1, because it's already b squared, and then minus, I need a bigger brush. Can I? I want to erase that. Yeah, I'm still learning the ins and outs here. So e squared 1 minus, that's better. E squared 1 minus cosine squared equals h squared. And we'll just remove this. I'll try to find a better process to do this, but in the meantime, now we also have b squared 1 minus cosine squared on this side, because we can subtract it over here, right? And yeah, so we can hoist it up. This is also b squared cosine squared. So we can bring it to the other side of the equation. We'll have b squared 1 minus cosine squared again. So we can substitute in h squared for that. And when we do so, we'll have h squared here and here. So we can also wipe those out. Also, we have w squared occurring twice. I believe we do. Yeah. I think I missed a step. Well, all we have left now is these negative signs, and they'll go away. But I'm forgetting something. So the 2's. I'm gonna have to back up. What did I do here? So I have w squared minus 2vw plus v squared equals h squared was minus v cosine plus v squared cosine squared. No, I think I'm actually wasting my time with this stuff on the left. I'm going to do this over again. Okay, so we'll work this out. H squared plus W squared minus 2W, 2VW cos, because we're expanding the squared, plus V squared cos squared equals W squared, which we can immediately eliminate, minus 2VW plus V squared. Now, the H, because this is V cosine theta, this is V sine theta, so we can just expand that as V squared sine squared. And now these two combine together because they're V squared sine. They're both V squared and they have cosine squared plus sine squared, which is 1. So that'll go away. So W's go away. And our V's go away. No, is this what I came up with before? It is, isn't it? Yeah, I'm trying to run. Well, VW cosine theta is actually what we want. And then what am I? Oh, right. So I didn't do a very good job explaining that, but when we subtract W and V, we're actually doing that. When we're calculating its length, we're doing that for the X and the Y. So whereas here, we're using the length. So this is actually WX minus VX and WX minus VY, but we're taking the length of it, so we're working all of that out. But when we expand it, we're not just getting VW, we're getting VX times VW, or VX times WX. It's a bit confusing, plus VY times WY. And so what this comes all out to is Vx times Wx plus Vy times Wy equals Vw, and those are the lengths of these two vectors, not just numbers, and then times cosine theta. And often you'll divide this, so it's on the bottom of this. And we can abbreviate this as V dot W. And this is called the dot product. And since it gives you the cosine, well, it gives you the cosine, but you never actually need to know anything about the triangle. You don't need to know the angle. You just need to know the vectors. And so if we only start, if we had no idea about this or about this, but we just had V and W. Well, we know these positions probably because we're, for instance, putting them on top of a rectangle. And we can work out this, the X times the X plus the Y times the Y to get this value. And then we can compute the lengths, divide by those, and that'll give us cosine, which, since we already have this length, we know this W length, and we know this V length. Because we know the V length, we know by dividing the dot product by the two lengths, we'll get the cosine. So we can, again, multiply by V and put ourselves here. Lengthwise, I mean, that'll give us the length to that spot. It will also, if this is a general vector, it'll overshoot if we, right? So if we started this at this position, we could scale this vector to move along it, like we were doing in the previous part, where we were going along the right direction, and on the up direction we were just multiplying by a scale factor. So it's the same idea here. It will move along the triangle along this direction by scaling the vector. But if the vector has a length longer than 1, then if we just randomly multiply, we'll move over somewhat. So we have to subtract. So we have to divide this vector by the length of W to normalize it. And after we do that, we'll have a scale factor of, because the cosine times the V, so that's V times V dot W over V W. Those are lengths. And we also cancel those V's. And then we normalize, so we have the W again. We have W squared on the bottom. And something convenient is that if you look at these XX, YY is equals V dot W, if both of these are the same vector, so W times W, we'll have WX times WX plus WY times WY, and it'll be the length of W squared. So this scale factor that will actually get us from here to here is often written as V dot W over W dot W. And this is called the component. And I guess terminology-wise, maybe that's the projection factor, projection scale factor, but we can start at this point if we call it P, and then add this times our W, and that'll move us from position P onto this bit right here. So, and that will be the same at, well, I don't want to say that. So what that does is it drops this point, if you call it Q, it flattens it onto this. And this is how we can figure out, if we know our W, we can treat our W as an x-axis. And we can flip this around, so we could have another axis up here, and we could do the same thing to drop it onto the Y. So what I want to do finally is demonstrate that. I mean, I don't know if I can come up with a good example, but I want to show the code gives you back the same numbers. So, how do I go about this now? So let's see. So So you would write something like this as x, dy, wx, wy, and project. So vx was our top vector, and w was the bottom. And for that thing we were showing, we would do dot ex, ey, wx, wy, and then if we just want to make things follow that, we could work these numbers out, but we'll just do what we did before and put them explicitly here. So this is the projection. Let's see, scale. And last of all, we'll scale our w vector. And in the, you can do that with raw vectors, but we'll usually be using displacements from a point. So v is displaced from p, but we'll take the projection of v onto w, and we'll add it to p like we did here. So we'll scale w and then add it to p, and then we'll put us on this position. Let's see how, what am I gonna, so I'll show this with p. Yeah. So I got to that. I had that base point, so I had put a circle there before, like so. There's this little dot here. I'm gonna get it. That's a little bit hidden, isn't it? I'll darken that. And it's being drawn last. So I'll draw it after the rect. Okay, so there. Now, what we want to do is go from, we had a, what do I want to say, these were the vectors that went to the center. Okay, these are going from base, but I want to, and these are going from below, but I want to go from, where do I want to go from? I think it'll work. I want to show that this, okay, so I'll start from here, from the blue point. That's what makes the most sense. So I'll go from here to the center. That'll be my v. And from here to here is my w. Right. So my base was this, but I actually want to start from here. So my 2, center x to center y would go from in the center of our second rect to back and from that top point. That's our v, and our w was the right direction because we're going that direction. So we'll figure out the projection of this. Onto right. And those are just the directions, so we want to add those to in there. So 0 brain is striking things out. I'm getting confused. And so we want the base again, so we'll just make this base 2x, base 2y. And we want to go from here to there. So we add the projection to that position. And we'll try again with a smaller circle that should go inside of this one. So I'll move that down a little bit. So the black circle should be on the outside, and then the smaller one, I'll just leave that white. Okay, now missed. Oh, because I'm assigning both to. There we go. So I was assigning 2x twice and then using it twice. But no, so that gets projected down onto that. And that's how you can go from a position in the local coordinate system the projection will give you the projection will actually give you the x or the y. We can do the same thing on this side, and in that way you can go from a global coordinate to a local coordinate. All right, that's about what I wanted to show today. So I'll actually went longer than I expected it to, but I'll leave it at that, and I'll see if I can get back to the procedural geometry and maybe the shaders not too long from now. So I hope anyone who's watching enjoyed. We'll see you later.